Back to ECN. Assume we are in this scenario with this router implementing ECN, perhaps also the destination implementing ECN, but S is not. So some users have a version of TCP that does not implement ECN. What will happen? Well, when this link is congested, the router will mark the packet header, and this mark will come back to S. But since S is not programmed to use ECN, nothing will happen. So S will not see any negative signal because the only signal that S understands is a loss. So what does it tell us? Well, it tells us that you should not only mark a bit in the header, but you should also know whether this TCP connection is reacting to ECN or not. Right? So you need this, and this is why in the ECN flags that we have in the IP header, we have in fact several things. We need to, so we have 2 bits in the IP header that are used for ECN, and those 2 bits, in a simple way, we could say one of the bits is saying whether this TCP connection, or this source probably, supports ECN, and if yes, the router knows. And the other bit can be used for marking congestion. That could be a simple way. This is not how things are. It's a bit more complicated. There are 4 bits. That means there are 4 possible values of the combination. And the 4 possible values are those. Either this connection, this TCP connection, is non-ECN capable, or the source is non-ECN capable. Or it is. If it is ECN capable, in fact, there are only 3 possible cases that occur. If this system is not supporting ECN, there's no point marking congestion. So in principle, we have only 3 possible cases. This flow is ECN capable and congested, or ECN capable or not congested, or it is non-ECN capable, and then there's no point marking anything else. So we have only 3 possible values, but of course, if there are 3 possible values in a field that can take 4 values, the engineers will use the 4 values. This is what they did here, and we will see the reason for that. So the 4 values are such that in total we can have 4 code points, non-ECN capable, ECN capable and no congestions, but there are 2 possible ways to signal this. So there are 2 values of the fields that use that, and they mean the same thing, and they are randomly chosen. They are randomly chosen by the source. When a source issues a packet, if the source knows it supports ECN, it will say, I am ECN capable, and it will, at the source, the packet is not yet experiencing congestion, so it will mark either this or this code point by choosing randomly one of the 2. When a router marks the packet, then it changes those set values to choose the value called CE. So in the case that I showed here, when the packet arrives here, the source had chosen ECT0 as a value of the source in the header. When it arrives at the destination, the value is CE. Right? Then this is echoed back, and in the echo back, which is now in the TCP header, used typically in an acknowledgement, there is 3 bits. One of the bits we will not discuss in detail. The first bit is the ECN bit, the equivalent of the DEC bit, that says, is there congestion or not? So it's an echo of this one. And there's another one which is used for verification. It's called a nonce, and we will discuss it in detail. The nonce sum was invented to solve additional problems that occur primarily because of what we call middle boxes. Example of middle boxes are NATs, and that is illustrative of what happens in the internet today. When the internet was deployed, there was no ECN. Then somebody comes and say, well, it would be a good idea to do ECN. But there comes the problem. The internet is deployed, and there are lots of boxes, routers, but also middle boxes that don't do necessarily whatever you would like to do. In particular, middle boxes like NATs, they tend to be very strict about what they accept or not accept in the packet header. So many NATs, they will, whatever field they don't understand, they will set it to 0 in order to avoid attacks that would be using covert channels, for example. You can use bits that are unused in packet headers to signal some information to, for example, a malware that is infecting your computer. And this principle of covert channel is what is used by botnets that are infecting computers to speak to this malware. So because of those security concerns, which are very severe concerns today in the internet, most boxes are very conservative. If they see a field that they don't see a usefulness for, they will kill it. So when those boxes were deployed, ECN did not exist, so they said this ECN field, I put it to 0, so if anybody manipulates it. Of course, now the NAT, you can probably upgrade its software, so you should not do that. You should not have this problem. However, you cannot guarantee it, so you will not have it. So it could be very well that everything here works perfectly fine, but before R receives the packet, because of a NAT on this side, for example, the CE bit is lost. So if the CE bit is lost, what will happen? Then it will be reset to 0, which might be interpreted wrongly by R as there is no congestion, for example. And then the whole story of congestion breaks. ECN does not work because the information is lost. This is one example. To avoid this, we require that there is some verification in the nonce sum. So the nonce sum is the sum of all the ECT, sorry, it's not ECN, it's the ECT bits modulo 2 during a congestion-less period. So here we see that when the source sends a packet, it puts ECT0 or ECT1. So it is putting a random sequence of zeros and ones. What the standard requires is that the receiver here, which is, what does the receiver see? It sees either non-congested packet, so it knows whether there's 0 or 1, or congested packet. So whenever, and there are typically periods of non-congestion with one or a few congestions, followed by periods of non-congestion. During every period of non-congestion, the receiver is required to send the sum of all the zeros and ones that it has received. And it puts them back in the nonce sum field of the TCP header. Now, what will that mean? Well, it means that if all the routers on the path are taking ECN seriously, then those values are not dropped, for example, then the value that is received by the source is the one that it can predict, because the source knows which zeros and ones it has sent, so it can know whether the nonce sum is the one that is expected. Of course, it's only a 0 or 1, so with 50% probability, you can cheat, but if you do that on a large number of packets with some probability that decreases over time, you will, the probability that cheating is not caught will decrease over the number of packets that is sent. So if some of the systems don't do what is expected, for example, if the destination pretends to be doing ECN even though the fields that it receives are erased, or it does not support ECN at all, then it will, there will be a mismatch here. In particular also, so that is in the case where the NAT box is dropping the values. If the destination itself is cheating, pretends to be doing ECN and does not do it, then this will also cause a problem, because if the destination receives things that are not ECN marked, it will not receive the CE, so it will not know which of the zeros and the ones, the CE that the destination receives are hiding away the zeros and ones that were sent by the source. So the destination that is cheating does not have the complete information, and with high probability, if there's a large volume of data, this will be caught here. So this is, well, for more details, I'll leave it to you to look at those examples here. It's a bit complicated because there's only one bit and that is sent. But this illustrates exactly the difficulties of fixing in the internet, in the public internet, changing the current way of operation. Here, the simple thing we would like to do is introduce ECN. We see that even to introduce ECN, we need to do that kind of heuristics with the non-sum to try to guess whether the path over which we do ECN is correctly implementing everything here. We have seen other instances where it's very difficult to change the internet. The most embarrassing today is IPv6. Changing from IPv4 to IPv6 is a dramatic change that is not happening smoothly. We'll come back to it towards the end of the course. When we do ECN, every router needs to estimate whether to mark a packet or not. So one way to do it would be to estimate what is the rate at which we are receiving traffic and compare that to the rate at which we are able to output the traffic, so the line rate. Right? That seems very easy. In practice, it's very hard to do on a short time scale. How do you estimate a rate? If you take a window of 0.5 seconds, at which rate are packets arriving? At such small time scales, packet arrivals are irregular. Packets are not fluid. They are discrete entities, so it's a bit difficult. There are ways to do it, but it's a bit difficult. Another way, which is used very often and is perhaps more practical, is to look at the buffer size. That gives you also an indication. If the input rate is less than the output rate, the buffer will be quasi-empty all the time. If the input rate is larger, the buffer starts to fill up. So the filling of the buffer is an integral indicator of the rate that you can, that comes for free. So this is what is typically done jointly with ECN. We need a function to decide whether to mark a given packet. And this function is implemented in what is called random early detection, RED. Here is a typical function that is used. So such routers estimate the average queue size by sampling every 100 milliseconds, for example, sampling the queue size at the buffer, at the output buffer. Then you do some smoothing to avoid two random quantities here. And this average queue size, smooth queue size, is put on the x-axis here through this function, and the y-axis will give you the loss probability. You typically find functions like this, where when this average is very small, you do not mark any packet. As it increases, you mark with some probability that remains small, and when it exceeds some threshold, you mark all packets here. This is a typical use, and you hope that through additive increase, multiplicative decrease, you will be operating in this region, because as sources receive negative feedback, they will decrease their rate, so you will reduce also the queue size here. Making sure that this happens in a real network is non-trivial and is very difficult to do. That's one of the problems with this story here. ECN is very little supported in the internet today. We will see an example where it's supported in data centers, but in the wide internet, it is very little supported. So what has been proposed, in fact, before ECN, is to use the same principle of RED, but without ECN, which may seem a bit contradictory, but you could use this curve here and say, instead of interpreting that as a marking probability, you interpret that as a dropping probability. Imagine you do this. That means you are a buffer, an output buffer in a router. When a packet comes, you go into this curve, and with a probability that is non-zero, you flip a coin, and with this probability, you decide to drop the packet here. And you would drop packets even if you do that, then the threshold, the maximum threshold would be the buffer size here. So of course, if you hit the buffer size, then you want to drop with probability 1 or close to 1. But if you're below, you will drop packets even though your buffer is not full, right? Which is apparently a paradox. You have a buffer. The goal of a buffer is to avoid dropping packets. Now you still drop packets. Well, this is an attempt to avoid the buffer bloat syndrome by trying to operate towards the optimal point where we give negative signal to the sources before the buffer gets very, very full. So this is what RED does when used without ECN. And it's called, in that case, it's called active queue management. So a packet may be dropped even if there is some space available. And the expected benefit is that we would operate closer to the optimal point of the buffer bloat curve because we give early signal to the sources here. Still, we have a buffer that can be used, in particular if the buffer, we need the buffer not because the rate is on a sustained way larger in the input than at the output, but because due to the randomness of multiplexing, there are many packets that come together, but it's an isolated burst. If that happens, the estimated average queue size will not be affected by this single isolated burst, so we will be operating, we are probably in this region. If an isolated burst of packet comes while we are operating in this region, we will still drop only a very small number of them, and we will buffer a number of them. In the best case, if we are operating in this region, we do not buffer any of the packets. We do not drop any of the packets, we buffer them all. So it's an attempt to use the buffers for what they should be really used for, which is absorb irregularities of traffic due to the randomness of multiplexing. But what we don't want is to use buffers to avoid a problem when the total input rate is on a sustained way for a long period of time larger than the possible output rate. So that's an attempt to get the both of this. So RED is deployed in a number of internet routers today. And this is if you, in the lab, in lab 5, we will see whether we can activate this or not. This is called active queue management, as opposed to the default policy, which is called tail drop. We drop a packet only when it's at the tail of the queue. Here, we drop it even before. Right. Voilà, we start seeing a number of complex things together. Small question. What happens in this case where all flows use TCP with ECN, all routers support ECN? What do we expect in terms of benefits? And the correct answer is the majority choice. We expect, if the thresholds of the RED function are well chosen, that there is no packet loss due to congestion in routers. In routers, because there could be congestion somewhere else. Where? In the application layer, if you have some application layer gateway. But things which may happen, but things that also happen even more frequently are the things that are below the network layer, the bridges. Right? So we also have queues, and bridges from that viewpoint are not different from routers. Now, bridges, normally, they don't look at the IP header. They don't know whether it's an IP packet or not, in theory. So if bridges are the bottleneck somewhere, then, of course, this will not work. Ideally, in the internet of next century, there will be only IPv6 routers. Bridges will be IPv6 routers. Everybody will implement ECN, and then there will be no packet loss due to congestion. But that's for next century, perhaps. I will not be here to verify, and you neither, probably. We will go through two more important things, and the other is very simple. That shows the importance of the problem, and in fact, it's an unsolved problem to congestion and performance in the internet today. Right? Although it works fairly well, but large companies like Google, Facebook, when they do measurement, they see that all the problems we mentioned about the performance of TCP, we would like to improve them. One of them is data center TCP. What is a data center? Well, if you visit one, which I hope you will do one day, it's a room with a lot of racks of PCs and switches. So it's walls of racks with wires and cooling. In the best case, fans. In the worst case, there's also water cooling. And practically, so the very large IT companies have them, but of course all internet services we receive today are probably hosted in one of these monsters. So what happens in a data center? In a data centers, there are essentially two types of traffic. There's a traffic from the outside, so a data center is providing a service to the outside, but there's also internal traffic in the data center. We will see when we talk about the application layer that there are things like load balancers, so there are application layer gateways that are inside the data centers. And there are things like also you're doing backup or synchronization. So you have a lot of very short flows that require low latencies, typically the user requests that come from the outside. Also internal things when you do computations inside the data center. And also flows that are very large that are when you do, for example, backup. And the problem is how can the two compete together, right? So if you are in charge of you're hired by Infomaniac and you have to take care of their data center, which version of TCP would you deploy? So Infomaniac will get ECN because the majority of you says TCP cubic and ECN. Well, TCP cubic is probably what you would get for free in the servers. In a data center, for the traffics that are inside the data center, TCP Reno and Cubic are probably providing the same because the latencies are extremely small. They're less than a millisecond, so probably doesn't make much of a difference. So B or D practically will not make a lot of a difference. But the important thing you want to do is to do ECN here. You don't want to drop packets inside your data center. Because you have control of everything, you don't have problems of cheating, you don't have problems of ECN flows competing with non-ECN systems here. However, this is not sufficient for some, and Microsoft and some others have proposed and implemented and deployed an alternative which is called data center TCP. And here what they want to address, so they do ECN, but what they want to address is avoiding the brutal multiplicative decrease by 50% here when there is a loss. We have seen that this creates those large oscillations that may cause the jumbo flows to take a very, very large time to get their fair share. And if they are jumbo but not too much, they will get less than what they could guess in reality. So the main idea of data center TCP is to replace the multiplicative decrease factor by something that depends on an estimate of the probability of congestion. How do you get this estimate of the probability of congestion? Well, if you use ECN, you can use it in different ways. The standard way that we've seen a minute ago has all those flags and non-sums and everything. Here they ignore all that stuff because we don't need that. We're in a controlled environment where a single company owns everything. Instead, we use ECN to estimate the loss probability simply by counting how many packets have a mark or not. For jumbo flows, the estimation will be very efficient. If you receive 50,000 packets, you can count which proportion of those 50,000 packets have a mark or not. So you can have a reasonable estimate of the congestion probability. And then the multiplicative decrease is equal to this. So it's adaptive. Now, if P is equal to 1, that is if you drop a packet with 100% probability, that will give us 50%. In all other cases, we will get something that is larger than 0.5, so the coefficient here is always less aggressive than TCP Reno or TCP or TCP Reno, let's say here. Now, if you compare, I mean, if in your data center you would have both data center TCP and let's say Reno or Cubic, doesn't make a lot of a difference here, what do you expect to happen? Well, the question is a bit tricky because if we compare to TCP Cubic, we need to know what the increase is data center doing. So data center TCP is doing the same linear increase as TCP Reno. It's not doing the cubic increase. So if we compare data center TCP to TCP Reno, we see that it does the same increase and a decrease which is less, always less, probably in average much less, because the congestion probability will not be 100% except for very exceptional cases. So it will get much less than TCP Reno. Since TCP cubic gets the less or more than TCP in this mode of operation, TCP cubic is not doing the same decrease, but is not doing the same increase either, and gets approximately the same as TCP Reno. So cubic equals Reno in this environment. The round-trip time is minuscule. Therefore, very likely, what we're going to see is that DC TCP, data center TCP, will get much more throughput, in fact. But in the data centers, all the internal connections are using data center TCP, so they compete with each other. As far as I know, the fairness formula has not been done by DC TCP, so if somebody's interested, it's a good research exercise to do. But what this tells us also is that data center TCP is not for the open world. It is for an environment where you control all the TCP connections. If you compete with the rest of the world, then you have a fairness and probably stability problem for the rest of the world. Now, in a given data center, there is both TCP connections that are your internal connections and the connections that come from the outside. They can be competing for some of the links and resources. So how can we solve the problem? What would you do? So the problem is you have two types of traffic, one that is using a form of congestion control, and one which is much more aggressive if it competes with another one, which is the one from the open world. You need to separate them. You need to separate those flows. Right? You can separate them by putting on different routers, different switches, different everything. But as you can imagine, we are smarter today. We can virtualize everything. And this is the topic of what is called class-based queuing. So in data centers, in many control environments, in fact, in cellular network, even in the internet, many operators do that kind of thing. So class-based queuing consists in virtualizing the service that is given to different types of traffic. For example, if you're an operator and you have TV distribution that is your own TV distribution, you're Swisscom, and you have Swisscom TV, you also have Netflix and YouTube TV. Perhaps you would like to give them different treatment to those, better treatment to your own because you get revenue for that. Right? So this is implemented in all routers. It's implemented in the Linux routers we have in the lab, but in all routers that also are hardware routers that are deployed by Cisco, Juniper, etc. So routers classify packets using some criterions. We will see in the lab, well, we will see in the labs in BGP in particular how to do that thing. They classify packets and associate a packet with a class. It can be based on any of the fields that a router is able to read from a packet. So it can be, for example, the IP source address. If traffic that comes from the Swisscom TV servers, we know what are their IP source addresses, for example. So that could be a very simple way to say all the packets that come from this part, they are for the video, so give them put them in a given class. Then each class is guaranteed a rate by implementing what is called a scheduler. Example of scheduler are deficit round robin. There are hundreds of different schedulers. A very simple scheduler is a priority scheduler. You have class A and class B, and the priority scheduler works as follows. Whenever there is a packet of class A in the queue, serve it, which means packets of class B are served only when there is no packet of class A. That's a very simple scheduler that has too many drawbacks. It's not used in practice. The drawbacks are, of course, if for whatever reason class A has a bug and sends a lot of traffic, class B is out, is not served at all. So you would like to give good treatment to your TV distribution network, but if there is a bug somewhere in a router that keeps spitting a packet, babbling a packet zillions of times, you don't want that your entire network is dead. You still would like that only this class is affected. So you have smarter schedulers that are doing, for example, what I said in terms of priority, but are also counting, for example, credits. I give a number of credits to class A, and I count how many times I have transmitted a packet of class A. And I see whether this credit is okay with what I expect. As long as it's okay, I continue serving class A. If the credit is too large, I stop serving class A. And while I stop serving class A, then the credit or the counter will be decreased here. And similar for class B, and by playing with the rate at which you increase or decrease the credits, you can guarantee some amount of rate to those two classes. Understanding that in more details, I realize would require much time. We won't do it. Right now, we just need the abstraction that says with class of service queuing, what the routers do, they allocate a rate to each class, and they guarantee, with some small uncertainty, they guarantee that this minimum rate is available to this class. Typically, this is also a minimum rate, but it's not a fixed rate. In particular, we allow other classes for borrowing that. Yeah, let me explain this on this example here. Here I'm showing 3 routers and 2 classes of traffic. One is streaming sensors, PMUs, that send data at 1 megabit per second. So this is an industrial network, if you want. In this industrial network, there are sensors that send using UDP at a constant rate, so they are not congestion control. And there is also a number of other flows that are TCP connections. Even in industrial network, you still have TCP connections for best effort traffic. For example, you may want to look at the log inside a machine. You may want to SSH into a machine to change its configuration. You may want to update a certificate or a session key. So you have typically the coexistence of those 2 types of traffic. When you have UDP traffic that is streaming at a constant rate, TCP congestion control does not come to play. So such a network must be what is called traffic engineered. For such a network, you must know what are the maximum rates at which all your sensors will be sending. You have to compute whether the sum of the rates is okay for the capacity that you have. If not, there will be what we have seen 2 weeks ago. There might be congestion collapse. You might have sources that send, that cause losses, that cause other sources to lose, etc. To lose, etc. So you need to do engineering. The result of engineering might be to do with class-based queuing. What are the parameters of the class-based queuing? So here, for example, we decided that we have only 2 sensors. In the worst case, we have 2 megabits of red traffic. So I'm doing a fairly brutal thing. I need only 2 megabits. Since I'm an engineer, I add 20%, and I give 2.5 megabits per second to the red classes. So I set up the schedulers here by saying this guarantees 2.5 megabit. Now assume this is an old style Ethernet or CAN bus type of link that is 10 megabit per second. The rest will be allocated to the blue traffic. Now, I want also to make sure that the blue traffic, I want to be completely safe, so I allocate to the blue traffic the delta, which is 7.5 megabit per second. In typical implementations, those are minimum rates, and whenever a class is not using its capacity, it's available for the other class. So if, for example, the source here is using at 1 megabit per second, de facto the available rate for TCP here is 9 megabit per second on this link. But it's guaranteed that whatever happens, it will always be 7.5. What could happen? Well, in principle, that should never happen, but if for whatever reason there is a bug in this sensor and it's sending at full rate at 10 megabit per second, then the red queue here will overflow, will lose a lot of packets because it will guarantee only 2.5 megabit per second at the output, and it must guarantee 7.5 to the blue. So therefore, it will serve that queue at only 2.5 megabit per second. So if this PMU, for whatever reason, has a bug and sends way much more traffic than it should, it will drop a lot, but the damage will be mitigated to this red fraction here. The blue will still get the 7.5. So the blue will get the minimum guaranteed and more if the rest of the other classes are using less than their fair share. Now assume PC1 and PC2 are transferring data to server 1, and to make the exercise simple, I'm assuming the RTT is 100 milliseconds, which means the latency is essentially in the last link or in the server here. Which rates will those two PCs achieve for each of their TCP connections? The correct answer is B. Right. Let's see why. So the first thing we could say, well, this is the network that we will see here. In fact, for the blue traffic, we have a link here, which is the effect of the scheduler on the blue class. That says, well, you have up to 9 megabit per second and at least 7.5 megabit per second. But we know from the outside the PMU is streaming at 1 megabit per second, so in fact it gets here 9 megabit per second. And here is the same, it gets 7.5 megabit per second, and in fact it will get 8 megabit per second because we know we have the two PMUs that are using this link here. And same thing here, we have 8 megabit per second. So in fact we have, from the viewpoint of the blue traffic, we have a network with a link at 9, 8 and 8 megabit per second. And now the question is, what will TCP do in a case like this? Well, that's one of the exercises we've done several times. TCP will maximize its TCP utility subject to those constraints. X1 is less than 9, X1 plus X2 is less than 8, X1 plus X2 again is less than 8. And in fact, the first condition is redundant because if the sum of the two is less than 8, then the first must be less than 9. So in fact, this constraint here, although it exists, it will never be a bottleneck link, so it does not appear in the constraints that will be active at the optimal. And therefore, it will maximize this subject to this single constraint. Now, whatever the utility, if the utility function is the same, which is the case because the RTT are the same, it will give the same to both, which is 4 megabit per second here. If you're not sure, you can compute the max mean fair allocation. You will find 4,4. The proportionally fair allocation, you'll find 4,4. Since TCP is somewhere between the two, if the two are the same, probably it should be the same as well. So this is what will happen in a case like this here. And we see that with class-based queuing, we have two things. We're making sure the red traffic, the PMUs, get exactly the performance they need. They don't see congestion collapse. If we did not have class-based queuing, there would be a risk that they get less, that they are affected by loss here. But we see that there's a guarantee that TCP will work well. We'll be able to get 4 megabits per second for each connection, whatever happens with the red traffic here. So this is the story about class-based queuing. Observe here that if we look at this network, we have 3 constraints, and one of the constraints here, 9 megabit per second, is a constraint that is never hit by the limit here. So that can always happen and typically happens in many cases here. The last topic in the last 3 minutes to discuss is very easy. It's all the other cases. We have seen 2 cases. We have the red class of UDP applications that are not rate control. They are an industrial application. They transmit at a constant rate. We don't want to change that rate, but we have to do traffic engineering to allocate to this class all the rates that it needs here. On the other extreme, we have TCP that adapts and computes implicitly the rate that corresponds more or less to a fair share of what the connection should get. Now, in the internet today, there's a lot of traffic that is not TCP. There's a lot of traffic that is quick. What is quick? Quick is an alternative to TCP. Formally, it's on the application layer, so it uses UDP, and practically all Google traffic is using quick, or if it can, it will use quick. So if you use Chrome, you will use quick to go to the Google site. If you use a YouTube app, you will use quick to download from the Google sites as well. An application like Quick, of course, Google is not stupid. They don't want to break the network down, the internet down, because a large fraction of the internet is theirs, is owned by Google, so they want the thing to work. So what they do is, plus they've hired half of the internet researchers, so they know what to do. So they implement congestion control. So what Quick does is implement the congestion control of TCP. The Quick exists in various versions. One is the official, the standard one. The other one is the original one of Google. In Google's original version, they used cubics. So they said, we want to be safe, so we implement exactly what people who know something and did it for TCP did. So that's the easy case, because Quick has the concept of packets, acknowledgements, it's point-to-point, it's not multicast, so it's easy to do. There are cases that are more difficult. This is if you have something that is of a very different nature. For example, a video streaming application that does not use TCP because it has real-time constraints, for example, for video conferencing. Then for such things, the concept of TCP with the acknowledgements and the windows are not working very well. What is done instead, in some of them, is what is the standard called the TCP-friendly rate control. And I will borrow 30 seconds of your break to finish with this slide. As you will see, the idea is very simple. This is for video application. Now, a video application can adapt its sending rate by playing with the resolution of audio and video. So we have a flexible rate. So such application, what it will do is will issue every second, for example, a report. It asks the receiver to send a report about how many packets, so the packets are numbered, like with TCP, how many did you receive, how many were lost, or if you ideally would support ECN, how many were marked. But in practice, it doesn't work with ECN. So how many have you received? I've sent you 1,000 packets, you received 995. Remember, for an audio or video application, they can live easily with a few packets being lost, so it's no big deal, but they keep a number of that. Now, the feedback is sent back to the source, and then the source applies the loss throughput formula we have seen, 122 times MSS divided by RTT divided by square root of Q, and it computes the rate that this application should send. And then, for the next second, the application will use exactly that rate. So it will not use the rate that is dictated by its Ethernet adapter or its codec or whatever. It will force the codec to use the rate that is given by this application, by the loss throughput formula. And if the loss throughput formula is correct, then it will behave very similarly to a TCP application. This is what we call a TCP-friendly application. Voila, we'll drop BBR. That does not work very well anyhow. So that's all for today. And for tomorrow, the program of the test for tomorrow is everything up to what we saw now.